Welcome back to The Explainer. Have you ever seen one of those cutting-edge drones lift off straight up like a helicopter and then suddenly blast forward like an airplane? It's honestly mind-blowing. Today, we're unpacking the exact AI and machine learning workflows that engineers are using behind the scenes to actually build these incredible machines.
The thing is, designing these VTOL, vertical takeoff and landing aircraft, is a total nightmare of competing physics. You want the flexibility of a rotorcraft, but you also really need the speed of a fixed-wing plane. Trying to balance that mathematically, it's incredibly tough.
To wrap our heads around how engineers tackle this complex math, we're going to follow a quick roadmap today. We'll start with the VTOL design challenge, move into the three-way tug-of-war, lay down the rules of the sky, explore the AI optimization loop, and finally, figure out how to find the sweet spot.
All right, part 1, the VTO design challenge, and a specific problem with transitional flight.
So combining vertical takeoff with efficient fixed-wing cruise flight is frankly a massive control headache. Think about it. When you hover, it's all about raw thrust pushing down against gravity. But when you cruise, you're surfing on the aerodynamic lift from the wings. That messy in-between phase, that is the transitional flight regime. It is notoriously unstable, with the airframe and the propulsion systems basically fighting a war against wildly conflicting aerodynamic forces.
And here's the kicker. The source material emphasizes that AI, specifically machine learning-based control, isn't just some fancy add-on here. It is the absolute enabling technology. A human engineer can totally calculate a perfect hover, and they can calculate a perfect cruise, but predicting the thousands of split-second micro-adjustments needed to survive that chaotic transition? No way. You absolutely need machine learning to step in and orchestrate that chaos in real time.
Moving right along to part 2, the three-way tug-of-war, and balancing competing priorities. You know how in engineering, you really can't have your cake and eat it too? If you want massive flight range, you need a massive battery. But a big battery means way more mass, which means bigger motors, which suddenly makes the whole thing a nightmare to actually manufacture. This brings us to a crucial concept called Pareto optimal. It simply means we've hit the absolute limit. You literally cannot improve the drone's performance without making it heavier or harder to build. The AI's entire mission is to hunt down these perfect trade-off sweet spots.
To pull this off, engineers set up a strict zero-sum game using a weighting budget. The coefficients for mass, performance, and manufacturing have to add up to exactly 1, period. If you want a massive bump in performance, you have to pay for it by sacrificing manufacturing simplicity or weight. By tweaking these exact percentages, an engineer can tell the AI exactly what matters most for their specific mission.
So all of this gets boiled down into a single master equation, the objective function. It takes your mass objective, your performance targets like endurance, and your manufacturing goals like 3D print time, multiplies them by those weights we just talked about, and spits out a final score. The AI's only job is to get that score as low as humanly or mechanically possible. It turns abstract design goals into cold, hard math.
Which brings us to part 3, the rules of the sky and establishing design constraints.
Because even AI has to play by the rules. For example, every single VTOL design must hit a thrust-to-weight ratio greater than 1.2 just to maintain a stable hover. The AI could invent a beautifully efficient drone that prints in 10 minutes, but if that ratio comes in at 1.1, toss it. It wouldn't even be able to safely lift its own weight off the ground.
And it's not just physics, it's the law too. Operational constraints might dictate a hard cap of 65 decibels of noise at a 50-meter distance. Aviation authorities like the FAA or ESA definitely do not mess around. A drone might be an absolute aerodynamic marvel, but if it breaks local noise limits, it's legally unflyable. Constraints ground our mathematical dreams in the real, highly regulated world.
So the system is constantly filtering out impossible designs based on performance, structural safety margins, aerodynamic stability, and even transport limits. Consider the manufacturing constraint for 3D printing, for instance, an overhang angle of less than or equal to 45 degrees. The AI knows immediately to scrap a structural design if a standard 3D printer can't build it without the internal supports just collapsing.
All right, part 4, the AI optimization loop, taking us from the problem to intelligent manufacturing. So, how does the machine actually do the work? First, it uses a statistical trick called Latin hypercube sampling to whip up nearly 1,000 random but totally feasible drone configurations. Next, it subjects those designs to incredibly intense physics simulations to test structural stress and aerodynamics. Then, and this is the real genius part,
Instead of running those heavy, time-consuming simulations millions of times, which would literally take years, it uses the data from those initial 1,000 designs to train a lightning-fast machine learning surrogate model. This loop relies on a strict feasibility classifier. It only passes designs forward if they have a 95% or higher probability of actually working in the real world. Think of it as the ultimate bouncer at the door of our design space. The trained model can glance at a new set of variables and instantly accurately predict if it's going to violate any aerodynamic or structural rules, saving a massive amount of computational time.
Finally, Part 5, Finding the Sweet Spot by Mapping the 3D Pareto Surface. After crunching all that data, the AI maps out distinct clusters of optimized designs at those trade-off knee points. You've got Cluster A, which goes all in on raw flight capabilities. Cluster B, which strikes a balance for lightweight, reliable builds, and Cluster C, which sacrifices some performance to guarantee incredibly rapid production. Because we map the whole Pareto surface, we don't get stuck with just one generic answer. We get highly specialized groups of optimal designs.
This categorization directly links your mission purpose to your manufacturing strategy. Say you desperately need that Cluster A drone for max endurance. Well, you'll be leaning heavily on advanced generative design, resulting in those complex, organic-looking airframes. But if you're pulling from Cluster C for a fast prototype, the AI specifically tailors that design for standard, quick-iteration 3D printing.
The big takeaway here is that there is no such thing as a single perfect drone. It's all about context. The AI gives you the absolute best possible machine for your exact priority, whether you need to fly the farthest distance possible or you just need to print the thing as cheaply and quickly as you can. This methodology perfectly translates human mission requirements into strict mathematical bounds, uses machine learning to survive the chaos of transitional aerodynamics, and hands the engineer a custom-tailored blueprint.
So, as we wrap up today's explainer, I've got a question for you. If you were the one funding this VTOL project, what's your ultimate mission? Would you bet on the long-distance marathon runner, the perfectly balanced featherweight, or the cheap-to-print prototype? The beauty of this AI framework is that whatever path you choose, the math has your back, ensuring your design respects the laws of physics while perfectly fulfilling your needs. Thanks for joining me on this deep dive. Keep questioning, keep optimizing, and I'll catch you in the next explainer.